All right, last section, parametric equations, implicit equations, and conics. All right, and you'll see a lot of these formulas are on that trig, the sheet that you guys are able to use on the exams. So if we had to graph parametric equations by hand, so let's first kind of look at an example. Consider a figure skater carving a figure 8 on the ice. The following figure shows the skater's path embedded on a coordinate plane. Is this figure a function? So the answer is no. Remember, to be a function, you should be able to pass the vertical line test. So this is not a function. At each moment in time, the skater is in exactly one location though. So technically, this graph doesn't always look like this because the skater is going to be here. They can't be all over the place the whole time. So in other words, the skater's location is a function of time. We can use a system of parametric equations to define the skater's location as a function of time. A system of parametric equations consists of a pair of functions, one that describes the x-coordinate and the other one that describes the y-coordinate. And typically the input value of these functions represents time. So if we let the x value be a function f and the y value be function g, where f and g are two functions whose common domain is on some interval of I, then we can say the collection of points defined by x and y is f of t, g of t, is called a plane curve. So the equation x equals f of t and y equals g of t, where t is in I, are called parametric equations of the curve, and the variable t is called the parameter. So again, when we're looking at this whole thing together isn't a function, but if we're talking about maybe an object or again a figure skater and where they're at on the ice relative to time, that's going to be, each of those points are going to be different depending on the time that's going on in their performance. So if we had to graph these by hand, you can see here, this is the formula for the skater's motion. So this is what a parametric equation looks like. You have your x variables defined by this function, and then your y defined by this function. So it's kind of like a piecewise function, but then not so much because we're talking about each x and y coordinate separately. So if we had to graph it by hand, what you're going to do is you're going to take whatever the domain is for the time. So here they told us that it's between it's for the first 8 seconds of the skater. So we're going to have the time be 0, 1, 2, 3, 4, 5, 6, 7, 8. So we can find these points. So to find, for example, when t equals 0, the x value is going to be x of 0, which is 4 times the sine of pi over 2 times 0, which gives us 4 times the sine of 0, which is just 0. And if we were looking at finding the y value, so again, your t is 0, so that's going to be 0, so that's equal to 8 times the cosine of pi over 4 times 0, which gives you 8 times the cosine of 0, which is 8 times 1, which is just 8. So that xy point is 0, 8. So that's where she would start. So if I were to actually graph this, we'd go to 0, 8 here. So there's where she starts. So there's t equals 0. Okay, now if we had to find t equals 1, you'd plug 1 in for t for the x formula. So 4 times the sine of pi over 2 times 1. So that's going to give you 4 times the sine of pi over 2, which is 4 times 1, which is 4. And then for the y value at 1 second, that's 4 times the cosine of pi over 4, or 8 times the cosine of pi over 4 times 1, which is 8 times root 2 over 2, which is going to be 4 root 2. So there, that point would be 4 root 2. So 4 is about right here. 4, so if this was 8, 4 root 2 is going to be about halfway there. So we'd show that and show that as our second point, t equals 1, so that we're showing the direction that the skater's going. So you're going to continue this on for t equals 2, 3, 4, 5, 6, 7, 8, and you'll end up getting the following values, 0, 0, -4, -4 root 2. So again, if I were to graph this, 0, 0 is here, so it goes from here to here. And then -4, -4 root 2 is going to be about right here. So you're showing again the direction that this skater is going in relation to time. So, or I guess the place that the skater is at. All right, when I put t equals 5, you get 4, -4 root 2. When t equals 6, you get 0, 0, -4, -4 root 2, and then 0, 8. So you can also graph these using Desmos. So to do it on Desmos, what you do is you kind of like type it like the x equation and the y equation. So we know that the x formula was that, the y was this, so that's how you put it in. And once you put it in with that t value, this will pop up where you put in the domain. So you put in the domain from 0 to 8, and you can see this is the exact formula that we had. Okay, another example. So suppose that x and y coordinates of the movement of a robot are given by that formula, and we need to find where t is the time in seconds from 0 to 3. Make a table of values and use it to sketch a graph of the robot's movement using arrows to show the path and the direction of the robot. Okay, so when t is 0, we get our x value is 6 minus 2 times 0, which is 6. And our y value is negative 2 plus 4 times 0, which is negative 2. So that point is 6, negative 2. So we'll plot that. So there's where they start. T equals 0. When t is 1, x of 1 is 6 minus 2 times 1, which is 4. Y of 1 is negative 2 plus 4 times 1, which is 2. So that point is 4, 2. So we're going to have, basically what we're going to do is we're going to take this, draw an arrow showing it went from t is 0 to t equals 1. Okay, so now we'll do the next one, t equals 2. So x of 2 is 6 minus 2 times 2, which is 2. Y of 2 is negative 2 plus 4 times 2, which is 6. So 2, 6 is right here. So we'll draw that with an arrow and label that t equals 2. So x of 3 equals 6 minus 2 times 3, which is 0. Y of 3 equals negative 2 plus 4 times 3, which is 10. T equals 3. So there that shows the path of the robot. It starts here. After 1 second, it's here. After 2 seconds, it's here. And after 3 seconds, it's there. Okay, so from the graph on the previous slide, we can determine that the robot is moving in a linear pattern. So it's moving kind of on a line. So by eliminating the parameter t and the parametric equations above, the parametric equation can be written as a rectangular equation involving only the variables x and y. So for example, we know that x is equal to 6 minus 2t and y is equal to negative 2 plus 4t. So if we want to write an equation in terms of just x and y, let's first solve this equation for t so I can use substitution. So I'm going to subtract the 6 from both sides and then divide both sides by negative 2. So I get that t equals x minus 6 over negative 2. Now what I can do is I can plug this into this equation so that I have a formula only in terms of y's and x's. So y equals negative 2 plus 4 times x minus 6 divided by negative 2. So that gives me negative 2 goes into 4 negative 2 times. So that gives me negative 2 minus 2x plus 12. So negative 2x plus 10. So the rectangular equation is y equals negative 2x plus 10. So now the hard part is figuring out what your domain is. So if you looked back, our domain was, our t's went from 0 to 3. So to figure out how that looks for the domain for x's, figure out what x of 0 is, and that's going to be the smallest, or could be. So let's see, 6 minus 2 times 0 gives us 6. And then x of 3 is 6 minus 2 times 3, which is 0. So your x values go from 0 to 6. And you can also see that looking back at that last slide, draw this equation, negative 2x plus 10, draw that line. So it's a line that has a y-intercept of 10, slope of -2, and you're only looking at the portion between 0 and 6 for the x values, and you'll see it's exactly what we had before. Okay, so we just looked at a linear example of a parametric equation. I'm going to show you now a circle. So if we were given this parametric equation, and we're given time in terms of radians, when we go to graph this, obviously you want to start at 0 and end at 2 pi, and then just do some points in between. So I'm just going to do these guys, just to get my table of values. So for example, when I let t equals 0, I get x is 3 plus the cosine of 0, which gives me 3 plus 1, which is 4. And then when I look at when time is 0 for the y value, I get 2 plus the sine of 0, which is 2 plus 0, which is 2. Okay, when I look at pi over 2 for being the time, I get 3 plus the cosine of pi over 2, which gives me 3 plus 0, which is 3. And then when I look at the y of that, that's going to give me 3 plus the sine of pi over 2, which is 2 plus the sine of pi over 2, which gives me 2 plus 1, which is 3. So you can kind of finish this out on your own, but you'll end up getting 2, 2, 3, 1, and 4, 2. So if I were to graph this particle, so we start at 4, 2, moves to 3, 3, then it goes down to 2, 2, then it goes down to 3, 1, and then it goes back up in a circle again up to 4, 2. So you can see that that ends up creating a circle. So we can express circles and ellipses as implicitly defined equations. So in general, for a circle, the parametric equations of a circle is this, and then the implicit equation is this. So again, the difference between parametric and implicit. So parametric is where you have formulas for both the x and the y. Implicit is where we're only dealing with these x and y values. Okay? So for example, if we had this as our parametric equation, like we did on the last slide, we could actually write this as so this is the parametric form for the circle. Here's what the circle looked like. We can actually write this implicitly. So again, that's going to be not dealing with different formulas for x and y. So it's one formula total by rewriting it using this formula. So it's x minus h. So the h value is the number, the constant, squared, plus y minus k. So the k value is this one, equals r squared. So that r comes from the constant that's in front of the sine and cosine, which in this case is 1, and 1 squared is just 1. So this is a circle that has a center of 3, 2, with a radius of 1. And let's double check that. Center of this circle is 3, 2. The radius is 1 unit, so that works out. So just another example, if I gave you this parametric, let's just say it's -2 plus cosine of t, and then the y, let's say is 5 plus sine of t. So if I were to write this implicitly, it's going to be x minus a -2, which becomes a positive, squared, plus y minus 5 squared equals r. So the r, the value that's in front of both the sine and cosine, is 1. So r squared, which is just 1. So that would be a circle centered at -2, 5 with a radius of 1. Okay, in general for an ellipse. So an ellipse is different than a circle in the fact that we have these values there. Okay, so an implicit equation for an ellipse centered at the point hk. So an ellipse is like a circle. It's basically an oval is what an ellipse is. So it's centered at the point hk, and we write the length of the horizontal axes 2a and vertical axes 2b is written like that. The longer axis is called the major axis, and the smaller axis is called the minor axis. So, for example, if I had to take this equation and I had to write this. So first of all, let's just look at, make sure this is right. So this would be a circle or an ellipse that's centered at 3, 2, which is correct. You can see that this unit here, which is the major axis since it's the longer one, is 5, which comes from that. The shorter axis, which is called the minor axis, is 3, which comes from that. Okay, so if we were to write these out, this would be implicitly, so we're going to use this formula with it. So it's going to be x minus h, which is 3, squared all over a squared. So your a is that value that's in front of the cosine. So 5 squared plus y minus k squared all over 3 squared equals 1. Now you will have these formulas on the final, so do not feel like you need to memorize these, you just need to know how to use them. So here is our parametric formula for this ellipse. Here's our implicit formula for the ellipse. Here's more examples. Sketch a graph of the following parametric equation where t is between 0 and 2 pi. So instead of doing our tables of values, which you totally can if you want to, you can just look at this and know that our center is going to be at 3, 2. Okay. Our axis horizontally is going to be 4. So 1, 2, 3, 4. So we go 4 in this direction, 4 in that direction. And then our vertical axis is also 4. So 1, 2, 3, 4 in that direction, 2, 3, 4 in that direction. So you can see it looks like that. And when we look at that, we can see that that is a circle. If I were to write the formula for this circle, it's going to be, again, that formula is it's x minus h squared plus y minus k squared equals r squared. The other way that you can tell it's going to be a circle right off the bat is because this r value is the exact same value. If those were different, that's when you're going to have an ellipse. So this is going to be x minus 3 squared plus y minus 2 squared equals 4 squared. So x minus 3 squared plus y minus 2 squared equals 16. All right, let's look at another one. So this one I can tell right off the bat is going to end up being an ellipse because these two values are different. So this is going to be, center is going to be 7, 4. And again, if you wanted to, you could do a table of values from 0 to 2 pi. And we're going to have, so 2 is going to be the length of our horizontal axis, so 2 in that direction, 2 in that direction. And then 5 is going to be the length of the vertical, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So this is going to be, I'm terrible at drawing these clearly. So that is our ellipse. Now, one of the things we do want to do is make sure we're showing the direction that it's going if this is a parametric equation. So I always recommend do figure out that starting point. So it's going to start at 7 plus 2 times the cosine of 0, which gives us 7 plus 2, which is 9. So this is where it ends up. So the x is 9, which is right here. So this is t equals 0. I'm going to just look at t equals 1, figure out which point that is. Or sorry, when t is pi over 2. So when t is pi over 2, I get 7 plus 2 times the cosine of pi over 2, which gives me 7 plus 2 times 0, which is just 7. So right here. So it's going in this direction. So we do want to make sure that we're graphing the direction when we are graphing these. So again, you can see kind of how I use my idea of knowing that this is an ellipse and then plotted points. If you didn't want to do that, you could go through the long way, which is more than fine, and just do our T's are between 2 pi and 0. So do those values for t and then figure out what the x and the y values are. And then if we had to find an implicit equation, so this is an ellipse, so it's going to be that x minus h squared over a squared plus y minus k squared over b squared equals 1. So that's going to give us x minus 7 squared all over 2 squared, which is 4, plus y minus 4 squared all over 5 squared, which is 25, equals 1. Another example. So now if we wanted to figure out the center, so we figured out what the center and the radius are if you're given it in this form. X minus h squared plus y minus k squared equals r squared. So when it's in this form, you can clearly see the center of a circle is hk and the radius is r. This formula here, though, is not in this correct format. So what we're going to need to do is do what's called completing the square. If you forgot how to do this, you may want to Google Khan Academy completing the square. This is from Math 95, which I know it's been a while for some of us, and some of us have actually never had it. So the first thing that I'm going to do is I'm going to divide both sides by 2, just so that I can get rid of this 2 being in front of the x squared and the y squared. So when I do that, I get x squared plus 4x plus y squared minus 6y equals 12. All right, this still doesn't help me because I need to get it in this type of form. So I'm going to figure out what value I need to add here